What'd you get on 47?
I don't have it.
Okay, so on number 22, and this is going to play out large later on. So you got these lasers. Now, and this is going to, especially when you get into what's called the photoelectric effect. And so what they figured out, and it was tough calculations, just the experimental process, was that, number one, these were photons. And this was a huge debate in the history of science, is that what is the nature of light? Is light a wave, or is light made up of little bundles of energy that's called photons? And that debate raged even back to Isaac Newton, okay? So one thought that it travels as waves is the idea that if you look at like a double slit experiment with light, okay, hey, the light comes in as a wave, and then it gets split apart, and then if you have a screen over here, you've got bands of different colors, okay, or different intensities. So if in this regard, light acts as a wave, and that's kind of the basic idea. Because the only way you can get this diffraction pattern on the other side, where you have light and dark bands, is if light is traveling as a wave. Because if you view it as being little bundles, like little particles, that get shot through, if that's the case, and if they were pure particles, and like imagine that you have a sheet of cardboard and you have two little openings and you're shooting BBs through this, and you're keeping track of where the BBs show up on the other side. Well, if they're BBs, you would only have basically two regions on the other side that said, okay, great, they're particles, because you don't get any kind of interference. So when they did what's called Young's double slit experiment, and they saw that diffraction pattern, they said, okay, well, this settles it. We're done. Light has to be traveling as a wave. Everybody's cool. But, and this is what we're going to start to talk about today, what's called the photoelectric effect. So the very short version, we'll talk a lot more about this over the next 3 days. The short version of the photoelectric effect is that if you have a piece of metal, lithium, sodium, pick your metal, and you shine a light on it, what will happen is that, and this is where you get into the different ons, okay? So you shine a photon on the metal, and if it's enough energy, it kicks out the electron and it goes flying off and you create a current, okay? So photons interact with electrons to kick out the photon, but there's a threshold. So in this regard, you can view a photon as being like this little bundle of energy, and this is what I was telling Lauren yesterday. Do not, it is a fool's game that will lead to pain, suffering, and potentially mind-altering drugs. Do not try and visualize the actual interaction between the photon and the electron. You can't, okay? We know it works mathematically. It works beautifully. The actual mechanism, we got nothing, okay? We don't. Because if you think about it, it's like, here's this little tiny bundle of matter that we've arbitrarily called an electron that has a negative charge. And along comes this light, which might be a wave or it might be a particle, we don't know which. And it somehow interacts with this electron. And then the electron goes, whoa, this is cool, I got energy, baby. And if you give it so much energy, it leaves its stable arrangement around the nucleus and it goes, deuces, I'm out. So in the story we're going to talk about, oddly enough, Cohen is going to be in jail, Okay?
Yeah.
Yes. So Cohen's in jail. And if we're going to spring Cohen out of jail, the judge has set bond at, say, $500. Okay? So, in the story, Cohen calls me, he goes, Bert, let's let bygones be bygones. Parents aren't going to help me out. I need you to get me out of jail. Okay?
I promise I'll never be annoying again.
Yeah, it's like, okay, whatever. So, that's the Cohen uncertainty principle right there. So, just telling you. So, if I show up with $499 and the judge sets the bail at $500, what's going to happen? Nothing. Cohen's going nowhere. Judge's going to go, nice try, but you got to have the $500. If I show up with the $500, then I get Cohen out of jail. So that's kind of what happens with the photoelectric effect. There's a certain amount of energy that you have to free the electrons. So this doesn't work if you have waves. Because if light is traveling as a wave, then they're not going to interact with the electrons. Or if it was a wave, what would happen, it would, in the traditional method of seeing this, if you shine the light on long enough, then basically if it was a wave, then enough of the waves would interact over a long enough period of time, and then the electrons would be like almost boiling water, where you would warm the temperature, and eventually, hey, the water begins to boil. So in the classical view, if light was waves, the photoelectric effect would happen if you shined it long enough. The electrons would gain energy, and then all of a sudden, boom, they're free. But that's not what you observe. You either see the photoelectric effect happening right away, or you don't. There's no time lag. So, at that point, we're going, okay, well, we thought we had it figured out. We thought light was traveling as a wave because of Young's double slit experiment, but then you get into the photoelectric effect, and this only works if light is a little bundle of energy that we're going to call a photon. And so basically, what we settled on is kind of we morphed the two ideas. That photons are particles, but they travel in waves. And so basically, it's the blending of the two ideas. So, when you get to, and all of that being said, when you get to question number 22. So on question 22 on part B, it's got rank in order from largest to smallest, the number of photons per second delivered by the three lasers. Now, the whole key to this is that you're told that it's kind of hidden within this, but what's common is that the power of each laser beam is 1 watt. So what's common is the power, okay, which is 1 watt, which is 1 joule per second. So I'm going to show you the kind of pure mathematical way to analyze this, and then I'm going to show you more kind of the simpler, hey, if you just think it through, it makes more sense. So if you look at power as energy per unit of time, okay, that's what you've got. So because you're dealing with photons, when you do that calculation of either E equals HF or E equals HC over lambda, if you combine wavelength times frequency and you morph it into this, that's the energy per photon. Okay, this is going to be important. It's a really, 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 really small number. Okay, each photon you want to make popcorn in the microwave. Okay, you put it in there. Basically, the microwave is emitting these photons, which you can't see, and all of a sudden, popcorn starts to pop because you've given the popcorn all of this energy, and it's warmed up. And pop, pop. Okay, can't see it, but we know what's happening. So you're kicking out all of these photons. You are not going to make popcorn pop by 1 photon. It's like, oh, 1 photon. Okay, we'll pop popcorn. No, it takes a lot of them. So if you do a little bit of hocus pocus, so the total amount of energy that you're going to need is the number of photons multiplied by the energy per photon, because technically that's what that is energy per photon. And then it's also a function of time because it's watts. So if you do a little bit of rearranging and you divide this by energy, so you get power over energy equals the number of photons per unit of time. But we also up here said energy was hc over lambda, okay? And that's equal to power over time. So if you do a little bit of rearranging, you get this. And then the lambda flips up and you get power over energy, which is this function of time. So here's what you want to look at. The hc part of that equation is going to stay the same. You're not going to change Planck's constant and you're not going to change the speed of light. That's a fixed value. So then if you look at this in terms of wavelength, okay, so if your wavelength is longer, okay, and this is the comparison that you need to make. So if the wavelength gets longer, and this is where we're going to morph these two ideas together. If the wavelength gets longer, what happens to the energy per photon? It decreases because of the fact that you're dividing by a bigger number. So if you want 1 watt, this is the amount of energy that you have. So here's the other way you can look at this. Let's say that you need $10. Okay, that's what you need. You need $10. So you can sell suckers at $1 per sucker, or you can sell a nice candy bar at $5 per candy bar. Okay? In which situation are you going to need to sell more items? The suckers, because you get less money per item. Okay? With candy bars, you only need to sell 2 of them. With the suckers, you need to sell 10 of them. So it's the same idea, is that you want, in this situation, 1 watt. You want 1 joule per second. So what's going to take more photons? The one with the more energy or the one with the less energy to obtain that 1 joule?
Less energy.
Less energy. But less energy corresponds with a longer wavelength or a shorter wavelength? Longer wavelength. So with a longer wavelength, you're going to have less energy per photon. So on basically your answers to 22, A and B should be inverses of each other. Huh? Like that? Okay.
I actually put down comments.
Okay. Now, when you get to 23, and this is going to be important when we get into the photoelectric effect, and this is why I want to spend time talking about this. So you've got the intensity beam of light is increased, but the light's frequency is unchanged as a result, which the following perhaps more than one are true. Okay? So let's talk about A, the photons travel faster. Yay or nay? No. The speed of light is a fixed value. Okay? What's the only thing you can do with the speed of light?
Make it slower.
Slow it down if you shine it through an optically dense medium. Okay? So it can't be A. Each photon has more energy. Yeah, Sean, you shake your head no. Why?
For the same wavelength.
Yeah. Okay? So intensity is basically, hey, how many photons are going to reach this per second? So let me show you how that works in terms of the photoelectric effect. So hold that thought. I got to switch over to that computer. Give me a second.
problem or a question?
Watts by your second. No, 30 minutes.
Oh, 30 days.
Yeah.
We're supposed to explain
Of
it.
course there's a stat for it.
Yeah, that's how many years
You didn't do that?
Then
I explained it.
you have to
Oh, which ones are true?
get number of joules you have to improve.
Wait, no, it should have been B and C.
So you have to,
Oh, which
Okay, fine.
yeah.
yeah.
I wrote the entire thing because the first one didn't make sense.
Yeah, I found energy per photon. And divided.
It was a really bad batch. We started.
Okay. So this is a good simulation, but yet it also really doesn't match what happens. So here's what you can do on this photoelectric effect. So there's some things that you can control. So let's talk about intensity first. So up there to the top, you can control the intensity. Then down here, you can control the wavelength. So what's happening is that you have a metal over here. You're shining a light on it, and this is going to be, light is going to have a certain amount of energy, okay, carried in the photons. The photons strike the metal. The metal has electrons. If the electrons interact with the photon, and the electrons gain enough energy, they go, hey, we're out of here, okay? So this is like me showing up, I have enough money to boast bond, Cohen is getting out of jail, okay? Because we have freed Cohen, right? So what I'm going to do is that I'm going to increase the intensity of the light. So I'm going to take that top bar, I'm going to slide that over. So when I slide that over, and let's go up to like 100%. So when I do that, what's happened to the number of electrons that are being kicked out? They've increased, right? So when I increase the intensity, I'm increasing the number of photons that are interacting with the metal. However, and here's going to be the difference. So if I take that wavelength and I shift it over here to like in the yellow. So notice that I've shifted this over to a longer wavelength. When I shifted that to a longer wavelength, what happened to the energy in the photons?
Decrease.
It decreased. Notice that with that, the current has stopped. So this is like Cohen needing $500 to get out of jail. I'm showing up with 480 going, hey, I was his physics teacher, you know, he's a good kid, for the most part. And the judge is going to go, hey, sorry, cash talks. So no matter what you do, it's not going to happen. So no matter what I do with that intensity, even at 100%, 50%, whatever, the intensity, even if I crank it up to 100%, that yellow light is not going to create the photoelectric effect. So, but that was kind of counterintuitive because they thought, okay, because again, the idea was that light was traveling as waves. And they go, oh, great. If we increase the intensity, then we should maybe still get to happen. Like, oh, we're going to put a lot of electrons in there. We're going to put a lot of photons in there. We're going to really increase the intensity. And that would be like me going to the judge and going, come on, judge, I really want you thrown out of jail. And the judge is going to go, booger off. You don't have the $500. No matter how intensely you ask, I'm not going to let Cohen out of jail. So, intensity is not a reflection of energy. Intensity is a reflection of the number of photons. Okay? So no matter how intense that bright light is, that yellow light is, 100% intensity, I'm still not going to create the photoelectric effect. But if there's a threshold, so if I lower that wavelength, shorter and shorter and shorter, okay, 527, okay, look. So I go to 527, which is kind of a green light. Notice that I start to get some electrons going across. So what that tells me is there's a break point. With yellow light, I didn't get any electrons being kicked out. With green light, I got some electrons being kicked out. So that's going to tell me that there's a threshold point in there where I can just kind of get those to come out. Now, here's the other thing that happens. You'll notice that this is a pretty steady stream. Now, this is where this reinforces the stereotype that's bad, okay? When you observe the photoelectric effect, you're not going to see electrons going across this gap. You're not going to sit there and go, oh yeah, there's some electrons, okay? And you're going to see the electrons. No, okay? You are not actually going to be able to see the electrons. What you're going to be able to see is a current that's going across. You're going to be able to detect a current going through that loop. So those electrons are going to get kicked out by the photons. They're going to leave and go, hey, we're out of here, and then they're going to go across. So here's the first two things that you can change. You can change the intensity, the number of photons, and then you can change the wavelength, which changes the energy of the photons. Okay? So those are the first two things. Then they said, oh, okay, right. So if I'm going to crank this down into like the blue region, okay? So notice when I crank it into a shorter wavelength, what's happened to the energy? It's increased. Now, but I'm still at 100%. The reason that I get more electrons being kicked out is because if you look at the structure of an atom, all the electrons aren't on the same energy level. For those of you that have just got out of the AP chemistry lecture, you know that some of those electrons that are closer to the nucleus are more tightly bound because of the fact that they are closer to the nucleus, a stronger electric force. So with Cohen, that would be like, in one situation, Cohen is really, really close to the outer wall of the jail. Hey, $500, I'm going to free Cohen. If Cohen is deep into the prison, okay, deep. It's like, where's Cohen? Deep.
Probably will happen.
And the deeper he is in prison, the more money I got to bring to free Cohen. Okay? So if he's deep into the prison, judge is going to go, man, that's going to cost you $700. Okay? So I can still free Cohen, but it's going to take more energy. So this is why when I shifted to the shorter wavelength, I got more electrons being kicked out, because then not only could I free the electrons that were towards the outside of the atom, I could also then free the electrons that were deeper in and closer to the nucleus. Now, realistically, from a lab perspective, it's incredibly difficult to like fine-tune the frequency of light. Okay, basically, hey, we got red light, we got green light, okay? We really can't sit there and methodically change the wavelength one thing at a time. But then they got clever and they said, notice down here I've got a battery. So I can either have, now if I crank this over here, you probably can't see it, but when I make this a positive voltage, this side over here, this plate now becomes, they were both neutral. Now I've made this positively charged, and I've made that negatively charged. So if that's positively charged, and that's negatively charged, why are those electrons hauling going across?
Electric positive.
Yeah, so they're going to be repelled by the negative, they're going to be attracted to the positive, and they're like, we're out. There's two reasons why it's going to go. They're going to leave the negative, and they're going to move over there, and they're attracted to the positive charge plate. In this situation, quick refresher. If this is negatively charged and that plate's positively charged, what's the direction of the electric field? To the right or to the left? Why to the left? The electrons are going that way. If you had a positive charge in here, the positive charge would be repelled by the positive and attracted to the negative. So protons go the opposite direction. So the electric field is moving to the left, but that's moving to the right. Now, an interesting thing happens. Notice that current is 0.15. If I increase that voltage like to 3.14, if I increase the voltage across the plates, notice that doesn't change the current. I'm not pulling any more electrons out. All that's happening is that once they are freed, then they really, really want to go to the other side. So this would be like, I'm going to free Cohen, okay? And Charles is going to be across the street with a bag of barbecued ribs going, yo, Cohen, I got ribs. So I'm going to free Cohen. Charles is going to be on the other side of the street going, I got ribs, okay? So Cohen's going to go running across the street because he's attracted to the ribs on the other side. Okay? Got it? Now, however, if I take that voltage, though, and if I make it negative, notice that the current effectively goes to 0. So now what's happening is that I freed Cohen, okay? I've gotten him out of jail. So on the other side of the street, someone's going, Cohen, I got tofu. See, where's that barbecue tofu? And Cohen's going, it's okay, I'm good. No, okay? So he's going to be repulsed by the thought of the barbecue tofu, which if you've ever had, I don't recommend it. Oh my God, I tried it once on a dare. Bam. Okay?
It's like a waste of time.
I still want to gag when I think about it. So here's the deal. If I make this negative, then I can stop that current. So this is what's known as the stopping potential. So from a physical perspective, we can fine-tune the voltage across the plates, okay? You've seen me do that when we have like the blue generator box, okay? I got a knob. I can turn that. I can increase or decrease the voltage very easily. I can't realistically fine-tune it. So here's where I can figure out. Let's say we're going to go back with Cohen, okay? $500 to free Cohen. I show up with 520. I got 520 bucks. I got to spend $500 of that to free Cohen. That leaves 20 bucks that I can give to Cohen and go, hey, go have a good time. So what's going to happen then is if I know that if it takes $20 worth of energy to stop Cohen from leaving the jail, even though I've freed him, I can figure out, how much excess energy did Cohen have when he left the jail? I might not necessarily know what's happening with me, but if I know, hey, this is what it takes to even stop Cohen from leaving the jail, I get an idea of that stopping potential. It's like Cohen's going, man, bad things are happening outside the jail. I want to go back to having 3 hots and a cot. I'm going back to jail. Versus Charles on the other side going, I got ribs. Okay? So, realistically, we can fine tune the battery to make it stop. Now, interesting thing happened. With this, it's tough to see back there, but notice that this is now negatively charged, and this has now become positively charged. So now, what's the direction of the electric field?
To the right.
To the right, because a positive charge would be drawn in this direction. These are electrons. So since these negatively charged particles, as they're coming over here, notice that some of them are still going. The current is still is showing zero, but it's got some particles going across there. But if I change that to say negative 0.40, okay? Still got some going across. If I change it to negative 0.8,
Let's just set to negative 50 and be done.
so now notice that negative 0.8, none of them make it across. So if I know how much voltage it takes to completely stop all of those, what that tells me isn't how much energy it took to free the electron. It tells me how much energy it has left over. And that's how much it's going to stop. So that would be like me going, hey, Burkamp showed up with $540. 500 bucks of it is what we call the work function. Work function is how much money I have to spend to free Cohen. The excess energy, what's left over, that's what Cohen's going to have when he leaves. So if it takes me $40 worth of energy to not let him leave, that tells me how much excess that we have. Okay? Kind of get an idea. This is why this is all kind of part of the same story. Okay. So you got a visual of how the photoelectric effect works. All right, cool. All right, give me a second. Now I gotta switch back. Hey.
No.
Okay. So when you get to, what question was that? 47. Okay. So if you look on 47, so what we're saying on 47 is that if you go outside and you have 1 square meter, okay, visualize this about 1 square meter, that's receiving 1.37 kilowatts, okay, per square meter. Okay, that's what we got. So what you're going to try and figure out is how many photons that is. So your answer to 47, first off, is going to be a really big number. Because each photon contains a tiny bit of energy. So if you look at what you're given on 47, it's saying the average wavelength is 680 nanometers for visible light. Now, think of how the world would be different if the sun only produced wavelengths of, let's say, that corresponded with, I don't know, green, okay? So the sun, let's say, only produced wavelengths that corresponded with green light, okay? So what that would mean is that there would be no other colors in the spectrum, okay? You would have green light, and that would be it. So here's where this would get weird, is that if you look at like Kevin's shirt being red, So what allows us to see red sweatshirt is that you have light being emitted that has all of the colors in the spectrum. So Kevin's shirt looks red because it absorbs every color but red. And the red is the light that gets reflected off. So this is where this would get weird, is if we have lights that don't emit red light, like let's say they emit every other color but red, Kevin's shirt would appear black because there would be no red light to reflect off of it. So what you see as a particular color is the fact that it absorbs every color but that. Now this is why, as going into summer, why don't you want to wear dark colored clothes outside on a bright sunny day? Yeah, they don't reflect well. They're absorbing all of that energy, okay? And it's like, oh man, that's going to get hot, okay? Black cars have black interiors or ovens because of the fact that they're absorbing that energy. Now, in contrast to that, you're wearing a white shirt. Oh, okay. White shirts are going to be cooler. Why? Yeah, reflect all that energy, okay, or a large portion of it, okay? Because white light is a conglomeration of all the other colors. So when you see as a color is a reflection of everything but that. So what we're saying on 47 is we're saying on average of all the radiation that we get from the sun, on average, it has a wavelength of 680 nanometers. So now if you know the wavelength, what can you find? Energy per photon, okay? Stop. So now you, speaking of lack of photons, so that was almost on cue. So if you can find the energy per photon, and you know how, and look at the numbers game, look at this from the unit's perspective. If even before you start to work this answer, you know two things. You know you're going to need a really big number because each photon carries a little bit of energy, and that's okay. It isn't like, oh, okay, everybody brace yourselves, I'm going to turn on the light. Because if every photon carried a tremendous amount of energy, it'd be like, oh, okay, all right? We don't carry much energy, but we have a lot of photons. So you know your answer is going to be a really big number, and the units have to be in photons. Okay, you want a number. So you got to get the energy to cancel out so that you're left with photons. So at some point in the story, you've got to take energy and divide that by energy per photon. The energy cancels out. The photons flip up, there you go. So even if you, at this point in your STEAM physics careers, you should be able to think through that and go, okay, yeah, right. I need photons. I got the energy to cancel out, and I need a really big number. That alone can just lead you to the process. Now, when you get to 68, so on 68, oh, come back here. So Voyager 2, Neptune's a long way out there. And 1989, it was 4.5 times 10 to the last kilometers from Earth. This radio transmitter, sent back in, okay, 21 watts of power. Assuming that the transmitter was equally in all directions, what's the signal intensity that was received on Earth? So, what you've got to use on this one, because intensity is going to be power divided by 4 pi r squared. So you got to change the kilometers into meters. So basically what we're saying is this. Here's the Earth. There's the sun. Here's Neptune way out here. And this thing is sending the signal back. Now, here's the problem. As that signal travels back, what's going to happen to the surface area that it's spreading out over? It's going to get bigger. So what's going to happen to the amount of energy per unit of area? It's going to get really small. Okay? So that's the other problem when you're dealing with interstellar probes. And it goes both ways. So in this situation, if we're sending the signal, if we're trying to communicate with it, and we send a signal out towards it, well, that's great. But when that signal gets there, what's going to happen?
It's gonna be a lot less energy.
Yeah, because of the fact that it's going to be so spread out. Because that energy is going to be on this wave front that's going to spread out. So the same thing happens with solar if you reverse the process. So if here's the sun, if you wanted to create electricity from solar, which planet should you be on?
Mercury.
Mercury. It's god awful hot, but that has the most intense light because of the fact that you're closer. Mars, you can still kind of make solar work around Mars. It's still further away, and that's actually what they used on some of the. They used solar panels on some of the rovers on Mars, which worked really well until they had a sandstorm, and then it covered the solar panels, and then it was like, oh, well, that really sucked. So now you basically lost the ability to recharge the batteries because the solar panels are covered with dirt, and there's no cleaning crew available to you. So once you get out to like Saturn and Jupiter, the light from the sun is so spread out that realistically it doesn't make any sense to try and use solar, because to get that same amount of energy, you'd have to have these big, massive solar panels to collect that small amount of energy because it's so spread out. And that's why they typically use like it's actually a small nuclear reactor inside of it. It's called a thermocouple reactor, nuclear reactor, and that's what uses it to generate that electricity. So on 68, that first answer on A should be a really, 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 really small number, like 10 to the negative 26th small. Okay? And then on B, it asks for what's the electric field. And so with that one, now that you know that intensity, you've got to use that 1/2 C epsilon naught and then E naught squared. And that answer on 68B should be 10 to the negative 12th. Okay? So, all right. Your answer on 40 in electron volts would make an GPA. Your answer on 42 in nanometers is around 300. On 26, that magnetic field should be something times 10 to the negative 8th. Are we good? Going once, going twice. So Danny, stop you on the camera, stand up, take